So I kindly request you to wait for some time. I will be just starting the session soon. Okay. In the meanwhile, if you have any doubts, you can just ask me. So are you able to hear me? So I think my slides are visible, right? So if you have any doubts, you can just ask me. Okay? And we'll just wait for some more persons to join before starting the session. In the meanwhile, if you have any doubts, kindly unmute and just feel free to discuss, because these sessions are meant to be interactive and for you to just speak up and ask your doubts. So if any doubts if you have in the previous weeks or this week, you can just unmute and ask me before I go directly into the session. And I also want the sessions to be interactive. So just feel free to unmute and just speak up, okay? Otherwise, these sessions don't have any meaning one way. So you can just ask the doubt in the time, maybe 2 to 3 minutes. We can wait and some more persons will join and then we can start the session, right? So in today's session, we'll be discussing the topics on digital circuits, basically on the logic gates, the Boolean algebra, and number systems also. And then we'll go into the techniques to minimize such expressions to actually make the hardware implementation more easy and simplified. That is the whole purpose of learning digital circuits in a perspective of the introduction to electrical engineering. So the basic aim will be to make you learn about the various techniques, simplification techniques, and the basic fundamentals of the Boolean algebra. So we'll just go into those directions and how to use those functions to implement that in the hardware by using the logic gates, and a basic on the number systems also. So before I start, I just want to ask you, because I continuously feel that there may be some doubts that you should ask. So are there any doubts? And can you hear me and see my screen? Just one of you. Yeah. So just I will move the screen. If you just have any doubts, kindly stop me anywhere and feel free to discuss. Okay. So I encourage the discussion at any point. So just briefing about the timings. We have these sessions actually every week for the weekly sessions, and we'll have such 13 sessions where the 12 sessions are of the weekly sessions. We discuss basic concepts and the fundamental numericals of every week to help you in various exams as well as solve the assignments, and one final extra session which will actually cover the all over concepts to solve the numericals from for the 12 weeks, all the 12 weeks, right? Like a revision session. So total 13 sessions, and all to be conducted on Tuesdays 7 to 9 p.m. with the same link that you have joined. So this was the basics, and if you have any doubts, kindly ask me and feel free to just unmute and speak up, right? Because otherwise I will not get what doubts you will have. I will just speak myself and will go away. That will be of no help to you, right? So always feel free to just unmute and speak up, okay? And obviously we'll cover the concepts through problem solving. That will be the best way to make you learn. Otherwise there is no point of these sessions, right? So just any doubts, asking again. Otherwise I'll go directly into the weekly discussions, right? Any doubts, any kind of doubts you have? Or I'll go directly into this week. I want to hear some voices, because unmuting is the best thing to do if you want this session to be interactive. So just speak up, feel free to speak, okay? Because these sessions are actually designed for you to be interactive. Yeah, any doubts you have, just ask, okay? Any concepts? No doubt? Okay. So we are in the week 7, where we are aiming to discuss various concepts on digital circuits. And to understand digital circuits, first you need to understand the word what the word digital means. So, do you understand what the word digital means? Yes, anyone? Before we go to the number system and all and the representation, the mathematics, I hope my voice is clearly audible to you and my screen is also clearly visible, right?
Yes, sir. Yes, sir.
So just if that is so, then just can you tell me what the word digital means? Because we are obviously discussing digital circuits. So you should understand it is something to do with digital electronics, right? And the circuitry part. Obviously, the week is related to circuits, and the whole course is related to circuits and all. But what the thing is that you have learned so much about analog and solved the network problems, right? But we are now moving to certainly the digital part. So can you just tell me what, just briefly or just very roughly, what you understand about the word digital? Any idea?
Digital means 1 or 0, sir.
Correct. 1 or 0, that is, you are speaking about the logic level. But actually, what the word digital, is there anything difference between digital and discrete and continuous you have heard of? Are digital and discrete same? I hope I am writing too small. So let me just, I hope it is visible.
Visible, sir. Visible.
Okay, so digital and discrete, any difference? Because we were in the continuous domain, right? Continuous domain, discussing certain things on analog, where we have a time varying function, maybe like this, maybe DC or AC, anything. We have discussed all the things as a time varying function, right? Which you call a or something forcing function, for which you get the response also. We give some voltages to a network, some black box, LTI black box, linear time invariant networks. We were discussing causal networks, and you gave some forcing function, let's say F1 of t in terms of voltage and current for electrical engineers, and then you get F2 of t. Someone asks you to calculate the response of the system in terms of voltage or current. Certainly, voltage across a node, current through a branch, all those things you have solved rigorously throughout the weeks. And you were being asked to calculate those things for some circuits where you have the forcing function also as a time varying function, and it was continuous. It was not discrete in time. And the response was also a time varying function which was continuous, not discrete in time. By the word discrete in time, what do you mean then? And you have understood, right? Where you have an analog function, then you have time varying functions which are continuous, and time is also continuous. That is, your x-axis is also continuous, and your y-axis, which you get as the response or the forcing function, all the parameters, all the quantities you are dealing with are continuous function of time. So that's why we say we are in the analog domain, right? But but certainly we then shift towards the digital domain. So what the difference comes here? Can you just tell me? Just briefly. Here the y-axis was fixed, right? Y-axis can vary, can take any values like 0.992, or at some time, let's say t equal to 1 second, because time is obviously continuous. You cannot break up time or have any function, perform any function over time, because time is not in your control. It is a kind of independent variable. So time is not in your control, but what the forcing function gives us, or what the response you can see as a function, as a time varying function, then I can tell that y is also varying randomly, but continuous value. It can take any values. The current can be 0.9918, or even the voltage can be 1.124. Like this. The currents can take any value. So we are still in the analog range, where we have a continuous function, any value. But what happens in the digital, can you tell me? You have quantized levels, right? We say as quantized. Quantized levels, not all the things it can take. It has certain levels. It has quantized, we say. Quantized into steps, like 1 or 0. In the digital domain, you know about 1 or 0, high or low. Obviously, they are related to some logic levels, right? Some logic levels. Obviously, in the physical world, don't have any 1 or 0. In the physical world, we may have some capacitor where we charge the capacitor up to some voltage level, let's say 3.3 volts or 5 volts, and we call that to be logic 0 or logic 1 for a high logic system. Or if the 0 volt is there, we may call it 0 for a high logic system. Or for a low logic system or reverse logic system, we may call this to be 0 or 1. That's up to us. But in the physical world, everything is continuous. So to make it digitalized or discrete, we have to get some or define some quantization levels where the network itself identifies the logic to be 1 or 0. And once we have this 1 or 0, the quantization in the levels of voltage corresponding to the logic levels, then we say we are in the digital domain, where we perform. Why digital is so popular or so easy? Any idea? Because it is very convenient or very easy to encode or decode the information in logic levels, in terms of logic levels. Otherwise, noise will distort your signals, like in the analog. So to prevent the system from incurring noises and other forms of distortion, we can encode the signal in specific terms to some logic level, where different logic levels indicate different form or different, I can say, values. And you can then extract again, you can encode the signal into digital form and then decode the signal. That is a better way of transmitting. For noiseless transmission or for any kind of distortion, to prevent any kind of distortion, the digital is very much efficient. And also, I can tell you it is efficient because the digital circuits consume a lot lesser amount of power than the analog circuit. Yes. So the control system you can actually build, the control part, which is a low power part. Obviously, they are all low powers, because in high power you have to go to analog only. So
information is stored.
Either information or some kind of signal conditioning. Some control system engineer will do digital control of the power converters, or some kind of PI controller you can design in digital form. Those are much efficient in the terms that the power consumption of those circuits are very less. Instead of you design some RC based PI controllers, how to actually in practice design PI controllers, you have two methods. You can use RLC elements, passive elements, to design the compensators or the filters, or you can have digital filters or digital compensators. So digital compensators or digital controllers, you can say, are very power efficient, right? Because we don't want as an engineer to consume much power for the low power handling control circuitry. The control circuitry actually handles a lot lesser amount of power. So we don't want to lose energy in those power systems, the control power systems, which are at low voltage and low power actually. So we can implement and go ahead for digital control, which will actually save the energy. Like in your AC also, the smart inverter technology is there. The control part is completely digital, right? Or in the IoT systems, you have cloud-based controls. All those control handles are digitally implemented to save the power actually. So it has low voltage and low power control circuitry. So we go for digital implementation. The digital architecture or the digital electronics architecture, which actually is built of transistors, TTL logics, and all those CMOS transistors are there, which consumes a lot lesser amount of power, because we can transmit the information using logic levels. And there are no power dissipated. Lot of power is not dissipated because the logic levels are controlled, I told you, by the amount of voltage, charge or discharge of the capacitors. And that is very low power. So we can go ahead for the digital control or digital logic implementation. And that's why we are learning the logic gates and the algebra also, to simplify the digital hardware, how to implement those logics in hardware. We need to learn the algebra because we want to actually further simplify the digital electronics architecture. So that's why we actually learn these number systems or the forms of algebra used to actually understand the working of the digital logic circuits. So that's why we learn Boolean algebra. So word Boolean architecture or Bool refers to it is a data type which is actually true or false. So true is indicated by 1 for a high logic level system, and then false we can encode as 0. and how the mathematics is actually working for those kinds of operations, where you have some rough idea how your system function will look like, and then you try to minimize the function to actually simplify the implementation and simplify the hardware architecture. So those things we'll actually cover. So basically we are into digital circuits today, and then first thing that comes into mind is that how the numbers in the digital world behaves. And to understand that, we have to change our number system, because now we are in a number system where we have zeros and ones, right? We don't have any other states or other numbers to actually encode the operations. So till now you were in the decimal domain, right? Decimal domain means where you have a 0 to 9, you have 10 numbers, and you then move to the base of 10, like in the zero base of 10 in the 0th place, then power 1 10, power 2 10. Like in the number system we go from units, then tens, then hundreds, as we increase the numbers, right? But we are operating in the base of 10. So base of 10 means that our numbers can be from 0 to 9. So we were in this decimal actually number system. But as you can understand, we have no 9 or 8 or 7 like that in the binary, right? We only have 0 and 1. So what can be the base? The base has to be 2, right? That we were only changing twice in one place, unit placeholder. Then again, if that is exhausted, that is 0 1, then we have to go to the next power, that is 2 to the power 1. So up to 2 to the power 0 we can toggle twice, 0 and 1. Then we have to go to the next 0 and 1. So then we have to actually change to the third power place of the base of 2. So that's how we do in binary number system. But actually there are also many types of other number systems, like the hexadecimal. Hexadecimal number systems are actually used for coding purposes. So that is also one form of system of representation of the numbers in form of hexadecimal numbers in the base of 16, or the octal representation where you have base of 8. The fundamental principle is same for everything, that you move in a cycle of 0 to n minus 1, where n is the base. And obviously you understand that if you have a binary number, then the base is 2, where n is 2, then you can move from 0 to n minus 1, or else 0 to 2. Understood? So you can understand that you have a base of 2. So you can just define placeholders like the units, tens, hundreds. But here the tens and hundreds will not matter. So like that in the decimal, there were zeros, tens, hundreds, then thousands. Likewise, here you have 2 to the power 0, 2 to the power 1, 2 to the power 2, because you are moving in the base of 2. And once you exhaust this place, you move to the higher place, like this. So you will move, basically start with, if you have a 3-bit number, we call that as the placeholders, right? So if you have a 3-bit binary number, you have 3 placeholders, and obviously if you move in these directions, your number value increases, likewise in the decimal system, but you are now moving in the base of 2. So here you can have filling with 2 values, 0 and 1, here also 0 and 1, so here also 0 and 1. So every placeholder m bits has 2 possibilities. So what will be the combination? How many combination of such numbers you can make if you have 2 values in every placeholders? So m bits means m placeholders, right? So how many values? How many values you can encode? How many values? Likewise, 0 I can encode with 0, 0, 0. Every placeholder I can fill with 0. Then the next placeholder of the m bits, I can assign the value 1. The second value I can assign to the next 1 1, then 0 0 0. You understand what I'm telling, right? Because 2, if you want the decimal value of 2 in binary, you have to actually do what? Fill this with 1 and then with 0. Then only you will get 2, right? Because 1 into 2 to the power 1 plus 0 into 2 to the power 0 will give you 2. That's why I filled this next placeholder, the second last placeholder, with 1, because we are moving from last towards the higher bits. Then likewise, how many possibilities will you have for the m bits? How many numbers, how many values can you assign? Or how many levels can you assign? Logic levels, anything. Because you are encoding certain states with certain values and assigning the bits accordingly. So how many bits? There are m bits. So how many numbers you can assign or encode with those values? Every placeholder, every bit can have two values, 0 or 1. So by combinatorial mathematics, what can you say? You have m placeholders and every placeholder has two choices, 0 or 1. Then how many total choices can you make? Or how many values can you assign? Because every value should be assigned by a different state or different binary number. So how many total values you can assign? Yes, there are m bits. But two choices per bit, 0 and 1, because you are in the base of 2 in the binary system. So how many values? Can anyone say? Just unmute and speak up. Feel free. Okay. Every placeholder, two choices. M bits. Then how many choices? How many? I can say different choices. Can you answer? Yes. Just unmute and feel free to speak up. Okay. Yes. I want to hear some answers. Yes. Any answers? Yes, please be free and just answer. Just think it to be a discussion, okay? Don't just get burdened with the thing that we are actually need to answer everything correctly. Yes, please tell me how many total values can you assign? Total different values, I can say. Total different values you can assign. How many? Every place of the bit you can fill either with 0 and 1. So two choices. So m bits. Every bit you have two choices. So how many significant different total values you can assign for the m bits? Every bit you have two choices. M bits are there. So how many? 2 to the power m, right?
2 to the power m, sir.
Correct. So 2 to the power m, significant total different choices. Like I take an example to show you. I have a 2-bit binary number, right? So 2-bit binary number means either you have 0, 0, 0, 1, 1, 0 or 1, 1. I can assign how many? 2 square values because the bit number was 2 and the base was 2. So base and bit number, right? Base to the power bit number is the total number of significant different values I can assign. Which assigns to 0, this assigns to 1, this assigns to 2, this assigns to, yes. So same, right? 3.
3.
So see, you have 4 significant different values or different logic levels you can assign. This 3 does not mean actually we want 3, some different logic levels I can say. For 3, you can have different logic functions or you can assign another logic function with this encoding. Don't think it to be some actual thing that is happening. We are encoding certain information into these logic levels or logic states. Like for example, you have a machine and you have a ball kept here. So for the logic level maybe 0, you can have the ball, and this is a kind of what I can say a lifting mechanism. So for the level 0, this ball will not be lifted. If you press 1 like a switch, this ball will be lifted here by the fork or by the arm of the machine, the lifting machine. So this 0 is actually not 0 but the state to hold the state of the ball to the low. And when you press 1, then it will lift it up like that, the logic high. So you are encoding two different informations using a single bit binary number. Likewise, you have the switch. Switch is actually operating in analog, but you can encode the information of two different analog states using digital encoding or digital numbers. Likewise, 0 and 1 are logic levels. So we encode different action states using the bits. And likewise, I showed you by the example. Similarly, if you see the decimal system are you you are already aware of. We have the base of 10. 10 means we have n minus 1 numbers, different numbers 0 to 9. And this you are already very aware of. Likewise, you have m, I can say 10 to the power 0, 10 to the power 1, 10 to the power 2. These are the placeholders. And for three place numbers or 3-digit numbers, what you say, we have certain m1, m0, m1 and m2. Then your decimal value becomes m0 into 10 to the power 0 plus m1 into 10 to the power 1 plus m2 into 10 to the power 2. Or we write from the left actually 10 to the power 0 into m0. How do you write this? We write like this. Then 10 to the LSB to MSB. Lowest significant bit to the highest significant bit, right? Then you have different namings. This is the highest order, highest, and then this is the lowest. Bitwise, we are taking m0, m1, m2 because the bits can move from 0 to 9. 10 choices are there. You can fill the bits or the digits with 0 to 9 or 10 choices because you have the base of 10. And other things are same as binary. In binary, you have 2 choices. In decimal, you have 10 choices. And you move in the higher order. We represent like that, okay? You go from left to right. But if it is in the decimal, then we go from right to left, right? Like 731, then we go from right to left, right? Plus, we need to do addition and then 7. For this case, we have 7 into 10 to the power minus 1 plus 3 into 10 to the power minus 2 plus 1 into 10 to the power minus 3. So the priority starts from the first, this part, in the decimal, in the fractional part, and from the lowest bit in the left for the whole number part. So you can write like 10 plus 0.731 and you can then break. Actually, you are getting that value only. So the 7 by, you can say how? 7 by, into 10 to the power minus. So 10 to the power minus 1 is 10 to the power 1 plus 3 by 10 to the power 2, like that. In fractional part, it is 0.7 plus 0.03 plus 0. Like that we write, right? Now in the octal system, all the things are same. How many ever bits you want to write, you can write, but you are in the base of 8. So in the base of 8, you can move from 0 to 8. So 0 to 7. So how many choices? 8 choices still you have, and other things remain the same. You have to move from start from this place and move towards the left to increase the order of the bits, right? Order means you have the power of 8. So m0, this is m1, this is m2, and this is m3. If I say, then I have m0 into 8 to the power 0, then I have m1 into 8 to the power 1 plus m2 into 8 to the power 2 plus m3 into 8 to the power 3 for the decimal. Right, for the decimal value. Or the decimal strength, you can say. Because we are in the power of 8. Okay. So hexadecimal, we have a slightly different architecture. We have 0 to 9 and then A to
F.
Yes. We are in the hexadecimal. So 10 plus 6. So 16 values or states. So actually what you do, you actually encode 11, 12, 13, 14 and 15 and 16 also as A, B, C, D, E, F. They are just representation, okay?
10 represents A.
Yeah. 10 represent A and 15 represent correct. Sorry. So 0 to 9 we are in the same values, and then A, B, C, D, E and F. 6 values we have in the alphabetical representation, but still they bears this value, right? They hold this value. Okay. 15. So these are the hexadecimal representation. Other things, you have 16 choices per placeholder, and accordingly you assign 2 to the power. So 16, we have 16 choices. So if you have
16 power 0.
So how many choices you can have?
16.
How many choice per bit?
16.
16. So if it is a m bit number, m bit hex number, how many total values?
0.
16 to the power m, right? Because 16 choices and then m placeholders. So for m bits, 16 to the power m values or action states you can encode within those numbers. So it is also used in the representation. So now we saw various number systems like the binary, which have a base of 2, and then we had the decimal, or I can write the octal, which has a base of 8, then the decimal, which has a base of 10, and we have hexadecimal, which has a base of 16. So now we know we have 4 different types of number systems which we are dealing with, right? But we have to actually learn the operation we have to do to convert or interchange among the various number systems. So if someone gives you some hexadecimal number and asks you to convert it into binary, you should be able to do that because it is very frequently needed while you do the coding, because you have to go from one language to another. The hex encoding, which you use in the microcontroller, and then you need to shift to binary maybe, or you need to again decode from binary back to decimal. So for the real world realization, right? Because binary is for the machine language. Then you have to go back or come back to the real world significance or real world value that you have put for your LED to control your LED 0 or 1. So that is logic level 0 or logic level 1. But if you are assigning some values maybe, then you have to come back from binary to that value in decimal. So you need to interchange. Should be able to interchange any system to another system. You should learn that. So let us see how to do that. So first let us start with easy things, right? So let us convert maybe one number I take from my mind. This was the 79 and we want to feed it to the machine. So we want to do the binary realization of 79. So can you tell me how to do that? Because we are now in the base of 10, but we want it in the base of 2, this decimal strength. So what we need to actually continuously divide.
Successive division.
Yeah. So successive division, and then we take the reminders. Reminders are actually the strengths of those placeholders, those power of 2. So actually you know that
30,
this is 39,
1.
and then you again do
1.
okay.
8.
Again you can do. How much time you will do till you find?
Reminder is less than the base.
Yeah. So actually you are reminded with 1. Right? Completely divisible. So you can write actually, because we have come to a place where the final value which is remaining, because the divisor is 1, so you cannot divide by 2. It is the remainder. It is becoming the remainder itself. So we move from the highest
bottom to top.
Bottom, because it is the highest order bit, and 0, 1, 1, 1, 1. So this is the decimal representation. You can also cross check how? 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power then 3, and then 2 to the power 4 and 5, right? So 2 to the power is 5 is 32, then you have 16, then you have 8, then you have 4, you have 2, and you have 1. These are all the decimal strengths. So you have a 1, then you need to add only those numbers which you have 1, because that is getting multiplied with the bit strength. So how much you are getting? 32 plus 8 plus 4 plus 2 plus 1.
79.
Yeah. So 44, 45, 46, 47. Yes. No, what we are getting?
40 plus 46 plus 47.
No, but we started with 79. We are missing one bit, right? I think we missed one bit. So this was 1, and then this was 19. Then this is 1. Then this is again 1. Then this is again 1. So we missed one bit, I think. So let us again do. 79 was there, right? I think we missed one bit. So just start from the top. Yeah, then 79 was there, right?
39.
So 39 reminder was 1, and then again 2. 19 reminder was 1, then again 2. 9 reminder was 1, then 4 reminder was 1, then 2 reminder was 0, then again 2
1
reminder was
0.
0. Yeah. So
0.
now you see 1 0 0 was there. So we missed one bit. See, this is 2 to the power 6 and 2 to the power 5 was 0, right? And 2 to the power 6 would have been 64. So now you add, you will get 64 plus 8 plus 4 plus 2 plus 1 will give you 79,
79.
right? Yeah. So 15, right? It is giving us 79. So just basically plug in 1 0 0, then 1 1 1 1 will give you 79. So this is how you convert from a basic you can say decimal number to the binary. Just divide with the base. And similarly, if you want to go from 79, now you already know the decimal form, right? Once you know the decimal form, you can go back to any other forms, because now you have the base of 2 and other bases are actually multiples of this base. Otherwise, if you want to go from 79 base 10 to something base 8, you can start dividing by 8. But you don't, once you know the decimal form, you don't have to do that hard work again, because other bases are in the order of that main base, which was 2. Because 2 to the power 3 was 8 and 2 to the power 4 was 16. So what you can do, you can group 3 and you can group 4, because you want what? They are significantly implying that they are in the base of 8 or 16. Why? Because if you group 4 for a digit for a binary representation, 2 to the power 4 is 16. So you are grouping in the order of 16, and you can take the value for that placeholder as the first order or the first place value for the 16 bit, or the first place value for the 8 bit, 8 base number, I can say. So what I meant is that if you have the digital representation of any decimal number and you want to then go back from binary to hex or octal, since hex and octal have the base which are of similar orders as that of binary, you can just, because hex is 16 and octal base is 8, which is nothing but 2 to the power 3 and 2 to the power 4. What I am saying is just group 4 by 4, because grouping by 4 and finding the value of that 4 placeholder digit in decimal will give you actually the strength of the first bit in that corresponding number system. So what I am telling, for hex actually what you can do, you can group by 4. So fourth place you can fill with 0. And then grouping by 4 will do what? Will enable you to find the value for that first placeholder, right, of the binary representation. So what is it coming? 1, 2, 3, 4 means what is its strength? Because we have 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3, which is nothing but 1, 2, 4 and 8. So 14, right? And what is 14 represented with hex? A is 10, B, C, D, E. So E, right? But you have 15, right? 8 plus 4 plus 2 plus 1. It is 15. So what can 15 go? 15 can go with F. So we have to fill F, because the strength of that bit is 15. So equivalent strength in hex will be F, right? Because 8 plus 4 plus 2 plus 1 is the strength of that bit. Because we are going now in order of 16, in multiples of 16. Then next higher bit, 15 to the power 1, will be this place. So what is this? This is nothing but 4. So 4 is 4. So 4f to the base 16. Why 4 4 group we did? Because that placeholder strength was 16, right? So because we are moving in the base of 16, we want the first bit to be encoded in the base of 16. That's why 4 placeholder grouped together for the binary to go back to the hexadecimal representation. And then again next 4 we take another set to actually find for the increased order of 16, right? Next order. So there we find 4. So you can also cross check by converting it to decimal, it will give the same value, because we already did nothing but changed only the representation. Number is still the same. It represents still the same number. Only the representation changed and the number system accordingly the base changed, right? So the representation changed. And for octal, what you did? You grouped by 3.
2 cubic, 2 cubic.
So 7 was the first bit, and then you take 001. So 1 was the next bit, and then again 001. So 117. And you can again cross check. What you can do, 7 into 8 to the power 0 plus
1 into 8 power 1.
And then
1 into
1
8
into
square.
8 power 2. So 64 plus 8 plus 7 gives you 79. So you are doing nothing but changing the bases, and accordingly you are changing the order of the number, right? Taking the numbers together, right? Which are nothing but why you can do this, because the 2, 8 and 16 are of similar. You can represent 8 with same power of 2, and using 16 also you can change with power of 2. So those things will be same. Just you have to group accordingly to place the powers in the same places. So now let us see the next part. Maybe some, we can say, what we can convert among different number systems. Let's say I give you 79.23 and I ask you to convert to decimal, binary, let's say. What you will do? Yes, what you will do? Just I added.
For integer 79, we will do substitution, sir.
So 79 we already did, 100, then
Yes. Now
1111, right?
for fractional value,
So for
0.23
yeah,
multiply with 2
0.23.
into
So
2.
why multiply? Why we are multiplying with 2?
So, no, sir.
We divided by 2 for 79, but why we multiply by
Don't know, sir.
so you need to understand the basic mathematics, what we are trying to do actually. So what you are doing actually in this representation, that you are doing least significant bit value times 10 to the power 0 plus least significant the next one times 10 to the power 1 plus m2 into 10 to the power 2, like that. But what is happening here? I can say f0 into 10 to the power minus 1
Minus 1.
into f0 into 10 to the power minus 2. Understood, right? What is happening in the digital representation? So when you are actually trying to go from decimal to the binary representation, what you do? You divide by 2. Why you are continuously dividing by 2? You are actually trying to divide by 2 to get the strength of that bit. Why? Because once you divide by 2 a number, let's say 10, and get the remainder 1, what it signifies? This 1 signifies a higher place or a higher order than the previous term. Because if you multiply with that many times, you will get back the number. So what I wanted to say is, if you continuously divide by 2, what will happen? Why we are doing like this and then moving up? Because you already divided the number 3 times, right? And once you divide the number 3 times and get a number, then again if you multiply that number that many times, you will get back the same number. That's why we are multiplying once that is a whole number, because we want to get back the same number with a remainder. Understood what I am telling? But in the base of 2, because 2 is the divisor, so always the reminders will give me lesser strengths than the divisor itself. That's why we are dividing by 2, because the base is 2. But number of times you are dividing by 2 means that whatever remainder is left, if you multiply that remainder that many times and add with the other numbers, then you will get back the original number. That was the whole point, right? We encode the number in the base of 2, but we want to get back the same number. So last number, how many times you divided, if you just power that up, you will get back the same number after adding with the different other reminders. We are just doing cross engineering, right? Reverse engineering. So there is a number system representation because we cannot go above 2. So we are taking the reminders as the strengths of that position, but we have to multiply that many times and add, keep on adding to get back the original number. That was for the whole number. But for the fraction, we need to multiply because fraction is itself lesser, right? So we need to do the reverse thing. Fraction is itself lesser than, or else you can tell what? There is no reminder in fraction, right? We have to take the whole number. So we need to do multiplication. Because it is already lesser than 2, you cannot encode with 0 or 1. But you want to encode with 0 or 1. But the fraction is itself lesser than 0 or 1, right? Oh, sorry, it is lesser than 1. So how can you encode? It is lesser than 1 but greater than 0. The fraction I am telling. So in order to encode with zeros or ones, you need to multiply actually. Why multiply? Because that will give me the strength of that bit, right? Because if it is coming 1, then that bit is of strength 1, but or minus 1. Because I multiplied 2, I need to reduce 2. Now here I reduce 2, I have to multiply with 2 to get back the same number. But here I reduced already, right? So I have to, wherever I am multiplying, see, I am multiplying here, means that I have to reduce again. So that's why the representation starts like this. Whenever you want to go back from binary to decimal, you have to reduce actually. That's why we are reducing, see. We are reducing, right? Because if someone asks you, what is 0.23 into 2? Say, you start from 0.23, right? And multiply by 2. Then you take 0.46. You again put 0 and again multiply by 2. What you get? 0.9. 0.9, again you get 0. Then again you go get 2. What you get? 1. Likewise it continues. But since you are multiplying 2, okay, you need to reduce 2 to get back the number. Why multiplying by 2? To get only the reminders, because reminders will give me the powers of those places. Then again, we during the getting back the number in the decimal, we need to reduce 2. And since we are dividing it by to get the powers of those placeholders, we need to again, since we are dividing, we need to multiply. So that's why the reverse thing works here, because this number is actually lesser than 1. But to encode with zeros and ones, we are actually multiplying to get the whole number, and then again in the representation we are dividing it. So number remains same. So the basic law is to keep the decimal value of the number same, but the representation comes with those binary digits. So that's why we do like this. Here the number will look like this only. In the decimal, we just remember the base is multiplied in the increasing order from this to this side. In the right side, the order increases, and we need to keep on multiplying and take out the whole number and just fill the digits of those particular placeholders, and then increase again by 2 by the base. Similarly, if someone asks you to calculate maybe ABD 0.75 B base 16, maybe to some tell me for hex, tell me for binary and tell me for octal, and also maybe some decimal also, like, right? So question is clear. ABD 0.75B, this is a hexadecimal number with a fractional part, and let us just convert it to all the three other number systems. So do this as an exercise. I need the binary part, the octal part, and the hexadecimal part, and also the decimal part. Sorry. So this is a hexadecimal number, right? So we saw how to convert the decimal to fractional decimal to fractional binary. Now we will see how to convert fractional hexadecimal to other number systems. The law remains the same. Like I told you that you have to first break this number down and then, but you have a facility here. You know already the strengths of these bits. So going from the hexadecimal to the binary is more easy. So can you tell how to go back? Because this is already grouped 4 by 4. I told you we did the reverse thing. We did binary to hex. Now we are moving back from the grouped hex, 4 placeholder grouped hex, to the individual binary representation. So what you do actually here, you just decode the individual values. What you do? Can you tell? What is D?
1, 3, 13. B means.
So 0 to 9, then A, B, C, D, E, and F.
10, 11, 12.
This is
E means
15,
13.
this is 14, this is 13, this is 12, this is 11, this is 10. Now you just decode, okay? Because you already grouped into 4, 4, right? During making the binary from the decimal. Now you just decode the decimal into 4, 4 group. So what is A? And 8, 4, 2, 1 you follow.
8, 4, 2, 1 code, sir.
8, 4, 2, 1. A can be written as 1, 0,
1,
1,
0, 1, 0.
The
11.
B is 11. So 1, 0, 1, 1. Then D is 13. So how to write 13?
13, 8, 1, 1, 1, 1, 0.
Then how can you write that? 1, 1, 0, 1.
Yes, sir. 1, 1, 0.
Then how can you group 7? 7 is 0,
0,
1, 1,
1,
1. Then how can you group 5? 0,
0,
1, 0,
1, 0, 1.
And then how can you group B?
B
B is
is
nothing but
13,
11. So B is, no, B is 11.
11, 11, yes, sir. 11.
So how can you group 11? 8 plus
1,
3.
0, 1, 0, 1, 1.
So we have actually decoded. So how to write? 1, 0, 1, 0, 1, 0, 1, 1, then 1, 1, 0, 1, point 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1. But we want also the octal. What to do? Since I have the binary with me, I can again regroup to the 3.
Fractal means 3-bit code, sir.
Yeah.
4 to 1.
But here you do like this. But the thing is that you need to follow 4 to 1. So kindly tell me what you are getting, these placeholders. What can I write?
101 means 5, sir. Okay. Yes, sir.
Okay.
Next 1, 2. 0, 1 means 3, sir. 0.3. 0, 5.
Right? Agreed?
Got it, sir.
Okay. So that's the very simple thing. We are first encoding in digital, in the binary. We had the numbers and we tried to go back to the higher order bases. We grouped according to the power of those bases because 8 and 2 are linked by a power of 3. So we grouped by 3. In the octal we did like this. So in the hex we did by a grouping of 4. But once you need to release that grouping in order to go back from the hex to binary or octal, we released and then again grouped again and wrote the thing. So it is very easy to regroup and group because they are all interrelated. But you have to do the hard work if you have to go back to decimal. So what you need to do now? Because you need to do calculations, right? There is a lot of calculations you have to do because now you are in the 10. So 10 you can write by A means 10 into 16 to the power, because you were in the base of 16 with a placeholder of 3. So 16, let us write like this: 16 to the power 0, 16 to the power 1, 16 to the power 2, 16 to the power minus 1, 16 to the power minus 2, and 16 to the power minus 3. And you had some values.
13 into 16 power. 16 to the power.
And how can I write this? Plus. So all these number strengths you need to add to get the decimal form. So 16 squared was A. A was 10. So 10 into 16 squared plus B. B was 11.
11.
Into 16 power 1. Plus C was 12. Sorry.
C not there, sir. C not there.
AB D.
D means 13.
So this was D. This was B. This was A. ABD I wrote. 16 power 0, 16 power 1, 16 power 2. Why? Because the base was 16 and the number was represented like that. So I broke down the number from the base of 16, right? So once I broke down, I have the decimal values or the strength of those numbers in the base of 16. So I get back the numbers because we are already doing in decimal, right? So once I release those bases, I get back the decimal form. Then I get actually 16 to the power minus 1 into 7, 16 to the power minus 2 into 5, and B was 11. So you can get back the number, decimal number. So just calculate how much you are getting. 10 into 16 squared plus 11 into 16 plus 13 into 16 power 0 or 1 plus 7 by 16 plus 5 by 16 square plus 11 by 16 cube. Just use a scientific calculator to calculate how much you are getting. You understand, right? Why is it giving me decimal? Because I am encoding the numbers with decimal numbers, right? 10, 11, 12, 13 is a decimal representation, right? In hex, you cannot use that. So once you use the powers of the decimal, right, you already get back the the decimal number, right? That's all. You already encoded and now you release the encoding in the base and you get back the decimal number. So what is it coming? I can do with you. Just let me do. It's important actually. One you need to continuously do. Then only you can just understand. One problem complete you need to do. That is suggested, right? So 16 square into 10 plus 11 into 16 plus I have 13 plus 7 by 16. So you get, then I can tell 5 divided by 16 square.
2749, sir.
Yeah, plus 11 divided 16 cube, right? 2749.4597.
Yes.
Just can approximate somewhat. So this was the whole art, how to convert from one to other. But interchanging was easy, right? But decimal you need to do the calculation. So I will just presume that you understood the whole concept. And if you are not comfortable, you can ask me to calculate anything, to go from one to another. Just if you want any further more examples, you can just ask me. You can just speak up and tell me which number system, from which number system you want to go from which number system. I can again explain and then take an example and just follow.
Sir, understood, sir, but I have small doubts.
Yeah, please.
Sir, in decimal to binary, 79 point some fractional value.
Okay.
Some 432. Sir, for decimal to binary conversion.
Okay.
For a fractional value, 0.43 into a fractional value.
Yeah.
0.4, we are multiplying 0.43 into 2, sir, during
correct.
Sir, 79 we are successful division for the integer value.
Yes.
But fractional value we are multiplying 2, sir.
Yeah.
You already told, sir, but I am not understood, sir.
What is happening? Why we were dividing by 2 continuously? Because 79 you cannot write in binary. Neither can you write 7, neither can you use the word 9. Because the binary system does not know anything related to 7 or 9. It does not understand. Binary only understand n minus 1. Base 2, n minus 1. What is that?
0
2 means 0 or 1. It does not understand anything other than 0 or 1. So what can help me? The reminders can help me put the strength in the power of those bases. The power of the bases will increase. But what is the strength I need to put in every placeholder so that I get a number like that which has a base of 2 is the reminder. And those reminders which are coming at the very next stages will be the higher power basis reminders. Because you already divided that many times, means that to get back the same number in its original form, bearing the same decimal value in the binary form, you have to again push the powers up. Because you divided, you reduced the number, right? And if you want to get back the same number, the whole number I am telling, you have to multiply.
Got it, sir.
But with what strengths are the reminders? That is understood. Plus some fractional part it had. But the fractional part also, the binary number system does not understand. Neither does it understand 4 or 3. So I need to again push the number to some understandable logics, 0 or 1. So let us multiply. Why? Because if we multiply, we'll get some whole number. That is also behaving like a strength, right? Because if that number is 0 point something in the next multiplication, then I can write that number plus that number divided by 2 because I multiplied by 2 in the next stage. So that's why 2 to the power minus 1 it went, or 2 to the power minus 2 it went. Understand? You are understanding what I'm getting, right? What I'm
understanding.
Because next power, why it went? Because we already multiplied it to the next power, the fractional part. So we have to reduce and write its power, write its strength. Strength is given by the whole number part because whole number part is either 0 or 1. You see, for a fraction multiplied by 2, the whole number part is either 0 or 1. It cannot be exceed 0 or 1. It cannot be 3 point something because we started with 0 point something. We can at max be 1 or 0. But we multiplied by 2, so we need to reduce in the next stage. So we went to the next lower order in the fractional sense. So that's why 2 to the power minus something. Because we multiplied, we need to reduce to get back the same number. But encoding it with 0 or 1. So that is the whole architecture we follow. To encode that decimal number into its equivalent binary form. But it should not lose its value. Whatever value was this should correspond to the same value. But with those numbers, 0 or 1. So that was the whole architecture we followed. First we powered them with 2 with the base. First we divided it and then powered it again. So value remains same. And here we multiplied it and then divided it in the number system representation. You see, here we are dividing because these places are multiplied places. So that's why we are dividing. This is division. 2 to the power minus 1 means dividing by 2. This is 2 to the power minus 2, which means divided by 2 again. Why? Because this is the next place, which we received how? By multiplying with 2 times. So dividing by 2 times will pull us to the same number. So that's how the number system is actually done. Understood?
Understood, sir.
That's why we are following such an architecture. Just remember one basic law. Any placeholder value cannot exceed n minus 1, where n is the base. So placeholder value cannot exceed n minus 1. So choose strength within n minus 1. That is the fundamental law of the whole number system. That strength of that placeholder of the corresponding bit should be lesser than the base itself. Otherwise, you move to the next order of the base. Base means a circular ring, where if you come to n minus 1, you again have to start with 0 or 1 or 2 up to n minus 1 in the next order, because the number system is following the base of 2. If you cross n minus 1, you move to the next order of the base. Next order of the base, we tell like that. Okay. So that's how number system is completely built up. That's why we are following this representation. Okay. This is just representation. Number value is same for all the places. decimal, hexadecimal, because that is the whole point. If you change the number itself, the things will not remain the same, right? We need to hold, or we need to actually develop the same logic levels for all the number systems, so that they correspond to the same action or same state, whatever you think of, think it as like. Okay, so just let us go to the very important thing, which is sign convention, right? So in sign convention, it is a convention we follow in the binary system representation, wherein till now you followed 79 base 10 was what? Just let me see. 100, then 4 times 1. But we did not think what to do if it is minus 79. How will the computer identify? So extra bit we put and mark it with 0 or 1, which exclusively I will code it like a way to let it choose the highest bit as the sign bit. If it sees 0, it indicates plus. It is not a mathematical operation, it is a simple representation. And if it sees 1, in the signed convention representation, it indicates just minus sign. No value or no strength. Strength comes from here, or the magnitude, however you tell. Magnitude, you can write it as 1, 2, 4, 8, 16, 32, and 64. Value you will get as 79. But the computer knows that this bit indicates minus 79. Like a way of representation. Simple, like that is the whole point, nothing else. So in signed convention of representation, extra bit or the highest bit denotes the sign, and remaining bits correspond to the magnitude. Only that much. Understood? It is as simple as that. But if you go to the complementary form of representation, then you have two cases. Like signed numbers may be represented either in signed bit representation, which I told you that the highest bit corresponds to the negative sign or the positive sign. And if it is negative, then highest bit is encoded as 1. But if it is ones and twos complement form representation, it is somewhat different. So let us see. So if it is a signed convention representation, highest bit 1 means minus. But it is not like that in the complementary form of representation. So if you want to encode 79, what is it? 100, then 4 times 1. But now I want it to represent in one's complement form. So one's complement is very easy. You just need to interchange 0 with 1 and 1 with 0. But why we are doing it? Just see. It will give you a very good essence, which you will not find in most of the books. Let me tell you. Just mechanically doing one's complement, okay? So this is one's complement. Of what? Of 79. Now what is two's complement? What is the method? Add 1 to the one's complement. Okay, you added 1. Now what is the thing that you are getting? In two's complement, you got something, right? This is two's complement. So what you got? Can you tell me? What is this? Can anyone tell me? So this is 1. What I can tell, this is 2, this is 4, this is 8, this is 16, this is 32, right? Yes, please tell me. Let me just see what is its decimal equivalent coming. So I wrote the number correctly, right? So 79, let me see. 100, then 4 times 1. Yeah. So if I do the ones complement, then I'm getting this. Okay. So if I take also the signed bit into consideration, let me add a 0 also. Then if I try to take the ones complement, this is signed bit taken into consideration, and then I take into the twos complement. What will I get? Try to find the decimal equivalent of this number. 1, 2, 4, 8, 16, 32, 64. Yeah, try to find. And this is 4 into 2, 128, right? So try to tell me decimal equivalent of this number and this number. Obviously, since this is a signed bit, it will go with -1, minus 128. So tell me what is coming. Minus 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. What is it coming? Just do and check. Yeah, you did, right? So I am doing something wrong, I think. This is only take the one. Only take the places which are 1, right? You are, I think, not corresponding to what I'm trying to actually tell you. Only take the 1 positions, right? But the highest bit, signed bit, you take with minus. This is in 2's complement form, considering the sign bit, because in plus 79 sign bit will be 0. You try to take the 1's complement and then try to find the 2's complement and try to decode the decimal number. That is what I am trying to tell you. So what it will be? Minus 128 plus 32 plus 16 plus 1. What is this? Just calculate and tell me. Minus 79, right? Please check and tell me. So if I assign an additional bit in 79 plus 79, which is 0 because the number is positive, and I try to find the 2's complement, then it inherently gives me the negative of that number. So in 2's complement representation, considering the signed bit representation, you inherently get the what? Negative of that number, right? So in 2's complement representation, considering signed bit, you get negative of that. That is the physical significance of 2's complement. But remember, you need to consider the signed bit. You need to consider the signed bit with the proper sign, right? Then only you will get the, so 1 denotes negative, get negative of the original number in decimal, right? Understood, or I need to repeat? Here I did not consider the negative, the signed bit. Here I considered signed bit and found 2's complement, right? Understood, or just I need to repeat? So if you consider signed bit for your original decimal number in the binary representation and try to determine its 2's complement, it will indirectly, or it will give you the negative of that number in the decimal strength. Is this clear or not? That is the physical significance of 2's complement. Otherwise, mechanically doing 2's complement is very easy. You just consider the number, break it down into binary, you flip the ones and zeros and add the last, add a 1, you get back a 2's complement. But that is not of physical significance. Physical significance only comes if you consider additional bit and then take the 2's complement. It will give you the negative of that number. Is this clear, or somewhat there is some friction? Shall I go ahead? Yes, shall I go ahead? Are you with me or not? I just want some answers. Okay, let us go to the digital logics. So as you can understand, digital logics, we have either true or false. How do we find is sign bit is not included or not? That will be told. That is the whole point. The system or the representation or the convention will be conveyed to you. How the encoding is done by the engineers. That is the whole point of the encoding. If you don't know how the encoding is done, how to decode? So obviously, humans are only encoding the information. So how the information is encoded, that should be known. Otherwise, it has no point. Otherwise, you cannot decode. If you don't know a code, how to decode? So the convention or representation should be known. Humans are only doing it for their own benefit. So the way of decoding is the inverse of encoding. So the way of encoding should be itself known. Otherwise, how can you know? You cannot just assume, right? Because assumption will lead you to the wrong conclusion. So it will be conveyed, right? And it is very much important to know how the encoding is done. Then only you can decode. Otherwise, it is of no use, right? So basically, what I was talking about is the logic gate, the significance or the evolution of logic gates, then how it started. See, logic means either you have true or you have false logic. So if a condition is false, then you call it false, and if it is true, it is true. Maybe the capacitor voltage VC is greater than 5 volts. If yes, then it is 0. If no, then it is 1. But if I say VC less than 5 volts, then if it crosses 5 volts, it is false. If it crosses 5 volts in the previous condition, it was true. Now, if it crosses 5 volts, it is false. So, reverse condition leads to flipped logic. It depends on how, it all depends on how the logic is set. Accordingly, zeros or ones will come. If the logic is reverse, then the flipped conclusion will come. So true or false doesn't have any absolute existence. It is all relative. How the condition is set. So first understand that. If you understand that, then you can understand there are two states, either true or false, based on a condition. So if it is true, we actually denote it using 0, and we define literals for that particular logic state, and which will encode or which will bear that logic information within a variable which we call it to be literal. So this is a literal or a term, you can say, but not a term. A variable is just known as a literal, and a group of variables constitute of a term in a logic or Boolean expression, what you see. So a function which encodes many of those literals, like for example, A bar C bar plus A bar B bar plus A B bar plus A B. These are all terms which you can see a group of literals combined together into groups in the product form and then added to form a Boolean logic expression, which is only representing a combination of logics which you can understand, because each of the literals I told you bears some logic information, and a group of literals constituting a term bears the information of a logic state, and those are also added to form the overall Boolean logic expression. So that is how the Boolean algebra evolved. But remember, all the literals are all only of two states, 0 or 1. So the mathematics here is not completely of the true algebraic mathematics, right? It follows a Boolean algebra, because in mathematics a into a is what? A square. But here in Boole, a into a is nothing but a, because if you draw the truth table of a, and a dot a means signifies that a will happen and a will happen. So if both are not true, then output will not be 1. So if both A and A are false, then Y will be 0. But if A is 0, A cannot be 1. So this state is not possible. If A is 1, other A cannot be 0. Always they will have the same nature, either 0 or 1. So if now A becomes true, which you encode with 1, then obviously Y will be 1, because A and A. 1 and 1 is obviously 1. 0 and 0, that is false and false, will be false. False and true will be false, because what this AND operator means is that we want both the states to simultaneously happen. Now one state is false and one state is true cannot simultaneously be true. That is a false state. So combinedly, if one variable state or one literal state is at false and another literal state is at true, and if we want both the literals to or both the events to happen, in that condition it is false, because both the events are not happening. So that's why 0.0 is 0, because that is true, that is a false event. Both the events are false and you want both of them to happen, can never happen. 1 and 1, both the events are happening and you want both of them to happen, is true. So 1. Any one of the events 0.1 or 1.0 is not happening and other one is happening, then both of them happening chance is 0. That's why we follow A.A as A. Why? Because A and A, you can see this is giving me same input as A. If A is 1 and other A is 1, then Y is 1. So that's why we write A.A, which is Y is A. Otherwise, if A is 0, Y is 0. So whatever is A taking 1 or 0, Y is also taking 1 or 0. That is a simple, you can draw the I can say logic representation. Then A follows Y or Y follows A. Sorry, this means Y follows A or A implies Y. So this is simply a buffer which you can write represent like this. So whatever comes in comes out. Output is nothing but following the input. That is represented by a buffer. And again, if you want to represent ANDs, then of 2, then you denote by simply a AND gate. The symbol of AND gate is like this, where you want both of the events to happen, only then your output will be true. So output true if both events happen. Similarly, if you have a OR gate, then output is high if any one of inputs is high, like those. So you'll see individually one by one gate. The buffer I told you, if you have an input and if you have a buffer denoted by a triangular sign, then Y is equal to A. That is the logic expression, and the symbolic representation is like this for a buffer. And if you have an inverter, then you represent by a NOT kind of thing in a small circle which denotes the NOT operation, right? So if you have A, then your Y will be A bar, the NOT of that. So if you have A as 0, Y is 1, A as 1, Y is 0. So that is the truth table or the logic table of the input and output constituting the truth table, and you can write in symbolic form as this. So this is the inverter, where inversion takes place. Whatever input is given, inversion is happening, flipping, or wherever input is 1, the flipped output is got. We get the flipped output is derived, right? So now we get the OR and NOR gates. So what is OR gate? I told you, any one of the inputs is high, then the output is high, which means that if you have A and B and Y, any one of the output is high, then only the input will be high. Now both of the outputs are low, 0, 1, 1, 0 and 1, 1. Both of the outputs high, obviously input will be high. Both of the outputs are low, input will be low, but any one of the outputs high will constitute high. So that is the truth table of the OR gate. But the NOR gate is just the opposite, or you denote by NOR gate, A, B, or like this. So you get y, and you denote the Y as A plus B. So what is that? And A plus B in the NOR, in the OR, A plus B. In the NOR, you denote as A plus B complement, the opposite of A plus B. Or whatever was happening in the OR, you denote the invert of that as the NOR gate. So for NOR gate, what will be happen? Neither A nor B is high, then only output is high. So like this. Other places it is 0. Just the NOR operation, right? So that is how the NOR gate is actually performing. And the physical significance of NOR gate where we use, where both of the outputs low and we want the output, both of the inputs low and we want the output to be high. Then only we can use NOR gate. Because NOR gate gives us the output high where both the inputs are low. And OR gate gives us the input high where any one of the inputs are high. Understood? So AND gate. AND gate, I told you, AND gate is represented like this and denoted by A dot B. But AND gate gets high when both of the inputs are high. Then only AND gate will get high. So other states it is low. Only when both of the inputs are high or true, then only we'll get output as true. And the NAND gate is denoted with a small circular sign in front of the AND gate, and we just represent A dot B whole bar, where it signifies that output will be true only when both the inputs are false. Other places it is 0. So that is the truth table of the NAND gate. So the NAND gate, as you can understand, becomes true only when both the inputs are false, unlike the AND gate. It is just the opposite of the AND gate. The NAND gate only gets true output only when both the inputs are false. I think you understand, right? So XOR or XNOR gates, exclusive OR, is high when both inputs are different, and it is denoted as A B bar plus A bar B, and it is symbolically represented like this, and the symbol is like this. So the truth table will be so when both the inputs are different, you can see different inputs where this and this, then only it will be 1. Other place it will be 0. That is the physical significance. Only when both the inputs are different, then only the output will be on or high or true. So you can check also that if A is 0 and B is 1, then only output is 1. Right? Because A bar is 0 bar into 1, which is 1 into 1, which is 1. If both A and B are 0, so 0 into B bar plus 0 bar into 0, which is nothing but 0. Or if A is 1 and B is also 1, then B bar is 0. And A bar is 1 bar, so 0 times 1, so it gets 0. Only Y is high when both the inputs are 0, 1 or 1, 0. Either different of the inputs, right? And exclusive NOR is just the inverse of the XOR and denoted like this, a small circle before the XOR gate, and it is just denoted as inverse operation of the XOR gate. And only when both the inputs are same, then only it will be high. Means that high when both are same, either 0 or 1, right? So if you draw the truth table, when both are same, right, then only it will be 1. Other place it will be 0. Just the complement of the XOR. Understood? And it is actually A B plus A bar B bar. So I will make you proof also that a b bar plus a bar b, if you take the complement, it will eventually come out to be a b plus a bar b bar, because this is what, this part is XOR, and complement of XOR is what you are getting as XNOR, which is nothing but this one. So complement of XOR is XNOR. That expression I will make you derive using De Morgan's theorem. So we'll actually do this exercise, but before that I have a small exercise for you. You have learned all the logic gates, right? Out of that, the NAND and NOR gates are special gates, which are used in almost all the electronic circuits, logic circuits, to actually build the other circuits. Because these are universal gates. Using these gates, you can construct the other electronic logic gates. Understood? You cannot construct a NAND using a AND, but you can construct a AND using NAND gates. Similarly, you cannot construct a NOR using OR gates, but you can construct a OR using NOR gates. Even you can construct an inverter using NAND and NOR gates. So that is the whole expression exercise that is given to you, that to build an inverter using NAND and NOR gates. Any idea? I have two inputs and I want the inverted output. How can I do that? Or say I have one input and I want a bar. How can I use NAND and NOR gates as an inverter to get a bar? Any idea? So here you have to use AND gates or OR gates. Any idea? NAND and NOR, I can say. How to use NAND and NOR gates to construct an inverter? It is easy, right? What is NAND? NAND is A, B whole bar. And what is NOR? A plus B whole bar. This is NAND, this is NOR. So how to get, if B equal to A, how to get A bar? Yes, how to get A bar? You just connect both the terminals and feed A. Then what will you get? A times A whole bar. And A dot A whole bar is what? A dot A is A. Why A dot A is A? I told you already that this event A will happen as well as this event A will also happen. That will only happen when both the events will happen. That is A. That's why A bar, right? So connect. Similarly, if you connect NOR, the same input A plus A whole bar, you will A plus A is what? A plus A is also A, and we'll get the same. So just connect the two inputs with A for a NOR or NAND gate, and we'll get an inverter. So that is how you do it. So just more implementation example. Let's say Y is A B bar plus A bar B. So that is what? That is nothing but a XOR gate. So you use inverters and basic gates to get this. Can you do? Let's say you have A, you have B. How can you use basic gates like AND gates or OR gates and NOT gates to get this? Simple, right? You take B from here and you take inversion of A and you do a AND, then you get A bar B, and you again take the inverter of B and you AND it with the direct of A. So here A comes, here B bar comes, here A bar comes, and B directly comes, and here you get A B bar, and you know you need to finally add A B bar plus A bar B. So you use a NOR gate, sorry, OR gate, and these are AND gates, and these are NOT gates. It's basically an inverter, right? And you get A bar B plus A B bar, because these are not these are OR operation, right? And these are all AND of the inverted and direct inputs. So this is nothing but a XOR gate. So inside a XOR gate, you can just simplify the logic as these basic gates. Hope you understand, right? Now we go to the combinatorial logic circuits, where the combinatorial logic circuit means you have a combination of literals represented in form of Boolean functions. So there are many inputs and the function you want to achieve. But remember, this is different from sequential circuits. Why? Because these combinatorial logic circuits don't require present system state, don't require memory, right? Present state by early states. This only depends on the present value. That's why combinatorial logics, right? Only the present value of the literals, and you will just do the maths and the algebra and the logic implementation to get the overall output of the function, right? So for that, using the Boolean function, if you see, you have some true terms as well as some complemented terms written in product and then sum form or sum of product forms. This is sum of products, and the product of sum form also is existing. So product of sum and some more function. So the Boolean function can either be written in product and then sum forms of the literals forming the terms, or the sum of the literals or forming the terms and then the products. So they are written as SOP and POS forms. You can just flip from SOP to POS and POS to SOP. That is why what we are trying to see. So the representation can be done in only two of the ways. That is in sum of the product forms or product of sum forms. No other representation is possible, because you will have to combine the literals to form the logic expression. And logic expression can be denoted in two ways: sum of product or product of sum forms. Up to this is clear, right? Whatever I am telling, I think is audible and everything is visible, right? You are with me up to this point, right? So I will just, so how they are actually formed, the SOP and POS, how you actually derive, do you know? These SOP terms are formed using sum of products of terms. So what you do, you take the literals A, B, C, D, you product them and you add them with other terms. So these forms a term, but they are product terms, and then they are added. The product terms you add either in the true or the complementary form to form the Boolean expression. So they are known as min terms. In SOP representation, where you have the sum of product terms, the product terms individually are referred to as min terms. And how to know which min terms to take to get the function is from the truth table. You have some, maybe A is, I am showing you a very simple example so that you understand what is happening. So this is very known truth table. It is of the AND gate. But let us see how to use the SOP form to determine the Y. So for that, you need to highlight the min terms. These are all individual min terms, right? And this mean term is known as A bar, B bar. Mean terms are always product terms, remember. A bar, B, where the value occurring in the true state is represented as B only, and the 0, 1 is represented as the complement. So what will be the next one? A, B bar and A, B. And you only need to mark only those which is coming true. You see, output y is becoming 1 only for the third expression, m3, fourth. So y can be written as sum of m3 only one term. And what is m3? It is ab. So y equal to ab. Similarly, let us take an example of another gate. So if you see, then 0 0 0 1 1 0 1 1, let us see. So this one mean term is, I told you, a bar, b bar. This one is a bar, b, and this is a b bar, and this is a b, and you need to mark those with 1. So this is m0, m1, m2, m3. How can I write y as a sum of product terms, but only those with 1? So m1, m2, and m3 are becoming 1. So m1, m2, m3. So what will they constitute? I can have y equal to sum of mean terms, that is sum of product terms. What product terms? Only the ones with 1, plus a b bar plus ab. Now can you simplify this y? You will actually get the NOT gate. Sorry, no, OR gate, right? The OR gate. So can you simplify? A bar b plus a b bar plus ab. Can you simplify? I want some answer. This can be written as, I want some answers, so I will do with different color. So now the problem comes to maybe simplify. So y equal to a bar b plus a b bar plus ab. How to simplify? You can use a bar plus a times b plus a b bar. I can write like this by combining this term and this term. A plus a bar and b taken common, then a plus a b bar. A plus a bar is what? Is 1. Either a will happen or a will not happen. That constitutes that eventually either of the events will be happening. So that is 1. And b, 1 times b is nothing but b. So b plus a b bar. Right? Then you can write it as a plus b. How can you tell me? By rule of redundant literal. How this is, I will just make the proof to you. But you remembered every time that a plus a bar times some term will be equal to a plus that term. So this literal is redundant. So we'll see that. Just for the time being, if you see some literal plus some other literal times the complement of that literal, then the term you write directly and the term with the literal, that is the complement of this term, gets redundancy. Is redundant, it is actually. So what it actually says, rule of redundant literal, this rule says that a plus a bar x is nothing but a plus x. So if I have a term or a literal and the complement of that literal times some other terms, then you can directly write that term plus the other term. The complementary term is redundant. So I will just say all these theorems to you in a short while. So it is nothing but a plus b. So we derived the expression of the OR gate. Similarly, let's derive the same using product of sum form. So we have a, b and y, and a, b and y I can say as 0, 0. Then for OR gate I can say it is as 0, 0, 1, 1, 0, 1, 1. So what is the max terms? Now let us write the max terms. Max terms are nothing but product of sum terms. So they are product of sum terms. So sum terms you need to write as the low terms. A plus b in sum form. And then again this is a plus b bar. This is a bar plus b and a plus b. A bar plus b bar. Because these are high terms. So in product of sum terms or in max terms, the sum terms, those sum terms needs to be encoded with the low logic. So if a is high, then it is a bar. So now this is denoted as M0, M1 capital, and whenever it is 0, you mark that. So it is a plus b. Same y becomes a plus b in the POS, but there is one term, so product of sum terms, but there is no other term to get product with, so just one. So product of sum terms. But you need to understand that one thing, that this when you write, and you try to write the max terms, you are actually writing the complement term, right? So y bar. So y bar is nothing but 1, 0, 0, 0. So just see one thing, if you would have taken the high terms, right? A plus b bar times a bar plus b to form the function, that would have been y bar. How you just see? What will it give you? A bar plus b bar a bar plus a b plus b bar. A bar a and b bar b are 0, because a will happen and a will not happen. Both will happen is event is 0. It can never happen that a is happening and a is not happening. So 0. And then you see you are getting b bar a bar plus ab. That is nothing but the complement of the actual function, because you took the high terms instead of the low terms in the max term. In the product of sum term, you have always to take the low logic level terms or the low output terms. If I took the one terms, likewise I did in the min term, I would have got the not of the actual function. This is happening because of De Morgan's law. And if you want to check that if y is a plus b, your y bar is what? Yes. Yes, so y is what? We determined, right? This is a plus b. So let us take. So what is De Morgan's law? I will just tell you, but let us just see it again. So what I told is that if you would have taken the max terms, right? Max terms are what? Max terms are what? Is product of the sum terms. We took always the low terms, where the output is low. And following the low logic level, that when you use max term, you only mark the zeros, and the logic you write as a plus b. That is a when it is 0, you write as a. So then we got y. But what would have been y bar is a plus b whole bar. And by De Morgan's law, a plus b whole bar is nothing but a bar dot b bar. Similarly, ab whole bar is nothing but a bar plus b bar. So when you break this not sign among the variable, this sign gets inverted with dot sign. Similarly, here was dot sign. When you broke the two, the dot got replaced by plus. So to break long line, replace plus with dot or vice versa. Now dot represents AND operation and plus represents OR operation. This much you understand. Now what I was trying to tell, that if you would have marked the ones, then what would you have got? A plus b bar times a bar plus b times a bar plus b bar. What I was trying to tell is that if you would have done like this, then you would have got y bar. So just check. You will be able to check this only when I tell you some more theorems, right? So let us take some more theorems later, and first try to make your grip over the, but remember, if you would have represented the high terms with the max terms, then you would have got the reverse inverted function. So up to this, just remember, I will make you prove this in a later stage. So just in the next some of the coming slides, we'll just prove these Boolean algebras. We'll just try to minimize. But before that will take approximately 5 to 10 minutes. I have 4 examples. But before that, let us understand some more fundamentals about the SOP and POS representation form. Some more, I can say, some more exercise let us do. Up to this, are you with me? Just confirm with a yes or no. You are with me, right? Okay. So what are we trying to tell? We are trying to derive a canonical representation from the truth table. That is very much necessary, because all we are doing is trying to derive some Boolean logic, y from a truth table. That is the whole thing we are trying to do. Now, this Boolean logic is a function which we denote as y, and it is a function of several terms or literals, right? It is a function of several literals. Now, there are two representations. Either this will be constituting of the SOP form or POS form of representation. But within each of the representation, in the SOP representation, I have sum of products. So maybe A, B, C bar plus A bar, B bar, C plus something, right? And in the POS form, I have product of some terms like A plus B plus C bar into A bar plus B plus C bar, like this. So what I mean as the canonical form is, in both SOP and POS, I should have A, B, C, that is all the literals present within individual terms. So if all literals are present in individual terms, then that Boolean function is a canonical representation of in SOP or POS form, whatever forms. But I need to have all the literals in individual terms. Then only it will be a canonical SOP or canonical POS representation. If not so, then it is a reduced order form. I can further reduce these things, right? In maybe A plus B, BC. Then each of the terms, each of the min terms, because these are product of some terms, sorry, sum of product terms. This is SOP representation, sum of product terms. But you see, this term is not containing B and C. So this is a reduced order non-canonical form. Reduced order simplified And once simplified, it does not remain a canonical. It is a non-canonical form. And for non-canonical Boolean functions, it is more difficult to find out the truth table, because you have to assume the variables or the literal states of the other variables also. So just let us see how to do it. Okay. What I am trying to actually explain, I will explain with an example. Then only you will understand what I am trying to tell. Okay. So what I am trying to tell is, let us consider if you have a three variable, right? A, B, C, and you have Y. Now I am giving you the truth table, for example. So the truth table is like this. Now these are all known, right? And you have the mean term form in sum of product form as M0, M1, M2, M3, M4, M5, M6 and M7. Now let's say M3, M4, M5, M6 and M7 are high. And in SOP, we take high terms with true logic levels. So I represent this as A bar BC. This is nothing but A B bar C bar. This is nothing but A B bar C. This is nothing but A B C bar. And this is nothing but A B C. So in sum of product forms, I will have Y as A bar B C plus A B bar C bar plus A B bar C plus A B C bar plus A B C. Agreed? Now if you try to simplify, then up to this it is a canonical form. But once you try to simplify, it will go to non-canonical form. Why I try to write this as non-canonical form, I will just make you see that you can just simplify how, but by maybe taking AB common. Let's take AB common, okay? Let's take AB common. And then C plus C bar will be 1. So we reduce these two terms. And now I have only a less term with a reduced form. Plus let us take which two term? Let us take these two term, okay? You see my marking. And let us take common A B bar out of these two terms. Again we are left with C plus C bar, which is nothing but 1 plus A bar BC. So what we are left with? AB plus AB bar plus A bar BC. Then further you can take A common and write B plus B bar plus A bar BC, which will give you A plus A bar BC. Now using law of redundant literals, I told you A plus A bar times some term, you can just take this variable as redundant. It will become A plus BC. But I will teach you these laws again with proofs. So if I give you A plus BC, let's say I give you A plus BC as Y, instead of giving this whole function. Are you with me till this point? What I wanted to do is, let's say I give you AB plus C or A plus BC, let us say. Okay. I think I am correct here. Let's say I am giving you Y equal to A plus BC. Then can you derive for me the mean terms from this? I don't give you the mean terms, like mean term can be represented also like Y equal to sigma 3, 4, 5, 6, 7, or product form of 0, 1 and 2. Both are same. Just we saw. You need to take the other terms in the max terms. So these are M0, capital M1, M2 in the low logic level terms. In the product of sum form or in the sum of product form, you need to take the high logic levels. The terms where the output y is 1 along with the high order true logic levels, right? So this is sum of product and this is product of sum. Now I am not giving you this because with this you can easily form the truth table. I am giving you a plus bc, which is nothing but the reduced form of this complete function, Boolean function. So what we did reduced it and found out that it is a plus bc. So if I give you a plus bc, I think the screen is moving. Yes. Now can you give me the min terms and form the truth table? Truth table and write SOP and POS. How to do it? Just wanted to tell you that. So what you can do, see, you have some terms missing of B and C, and you have some terms missing of A. So A can take either 0 or 1, and B and C can also take 0 or 1. But what this function is telling you that irrespective of the value of B and C, the output does not depend actually. The output depends on the value of A only, and A obviously needs to be true. So this will be 1 only, and B and C also needs to be true for this output to be Y. And the other value in this term does not matter. Similarly, this also does not matter. So what will be the term? 1, then B and C can be either 0 both or 0 1 or 1 0 or 1 1, doesn't matter. But this term needs to be 1. Along with that, how many other terms? Plus means odd. So how many more terms? Either 0 1 1 or 1 1 1. So what are these terms? Yeah. So what was the actual function? Let me see. Actual function was a bar bc plus a b bar c bar plus a bar bc plus a b bar c bar plus a b bar c plus a b c bar plus a b c. So we did what? We did the combination of these two terms, AB and then C plus C bar, I am not writing, and then AB bar, again C plus C bar plus A bar BC. And then we did what? We took A common and B plus B bar was 1, A bar BC, and we got A plus BC, right? So coming here, we got how many terms? So some term you can see is repeating, right? This 1 and 1 are repeating. So we'll not take it twice. So let us write the terms 1 0 0, 1 0 1, 1 1 0, 0 1 1. And obviously 1 1 1. So we have 5 min terms. And can you tell me what are these? This is M7. This is likewise I can write 1, 2 and 4. This is M4. And this is what? M5. This is M6 and this is M3. So M3, M4, M5, M6 and M7. Same value, same we can get as 3, 4, 5, 6, 7. You see, I got the same thing, 3, 4, 5, 6, 7. Understood, right? So I told you the technique, how can I reconstruct the truth table from a reduced order simplified function, but I still did not tell you how to reduce it or how to simplify the Boolean expression. So I will take maybe just 10 more minutes. I told you already this, right? So now finally we come to the stage that we'll explain how I am doing all these simplifications for the various Boolean expressions that you need to understand, and this will be very important part of the lecture. So not operation, and operation, or operation, I already explained. Are you with me still up to this point? So now I will explain you the technique, how I am doing this, and I will prove the expression what I was deriving there. So are you with me till this point? I will do it fast because now you will understand what I am trying to do. So just tell me with a raise of your hand. Okay, I got the answer. Okay, thank you. So now you will understand what I am doing. So now you understand one bar is 0. Obviously the not operation is what? The not operation is inverse of the logic state. So just let me unplug. Yes. So what is one bar? One bar is nothing but 0. And what is 0 bar? 0 bar is nothing but 1. So we call this not operation. And obviously a bar we denote as complementary operation. And we know a dot a is a plus a is a. And a double bar is nothing but a. Complement of the complement of a is nothing but a. So these are fundamentals, right? So or operation, if you do for the same variable, you will get the same variable. Otherwise, the AND operation also holds true for the same variable that you are trying to do. These are very fundamental relations. Now the commutative and associative laws. Associative laws are the laws where you can actually associate the or spread the bracket among the other variables, right? You can distribute it. And same thing goes for the AND operation. These are associative properties. And commutative means you can interchange, like a plus b is nothing but b plus a, or ab is nothing but b dot a. These are commutative properties. So this holds true, right? But you must understand that a bar b and a b bar are not same. Similarly, a plus b bar does not means that you are at a bar plus b. So here the properties does not hold true, right? You cannot interchange. So the distribution theorem, now we come to the distribution theorem, which is very useful and fundamental theorem. So let us understand it with an example. A plus b times a plus c, when you have same variable into the bracket, you can just simplify it with the variable plus the product of the other two variables. This is the theorem. Now let us see how this theorem works. You can break this bracket. A dot a plus b dot a plus a dot c plus b into c. Now a dot a means, or you can take a common from these three terms. It gives us, so let us take like this. A dot a means what? A plus ba plus ac plus bc, and take a common, then 1 plus b plus c plus bc, and you know that if you OR with 1 b and c, then you will get 1, and a dot 1 is a, so you get a plus bc. That is the proof. So in distribution theorem, remember, if you for example have a plus b plus c, and if you have a plus b plus d, then you have this a plus b common, then you can write a plus b plus these two product form cd. and it works both in product of sum and sum of product terms. So in sum of products, you understand, right? If I likewise, if you want to maybe use that, let's say a plus ab plus abc plus abcd. Let us take an example like this, and you understand that I take the a part common. Then what will happen? 1 plus b plus bc plus bcd. Then you see I take the a part common, and then you get a in the reduced form, right? Because 1 plus other variables will be 1. Then the distribution theorem, what it says, that you take the common variable and product the other. And the proof is like similar, right? That 1 plus b plus c will nothing be 1. So another example, maybe I can tell you a plus b bar. So this is one example, this is another example, and this is another example. This is the proof. And the example, if I give you, then you can write it as, see these two terms, you have a common, right? So you can write a plus b bar directly, and you have a bar common. So you can write a bar plus c bar. B bar and c bar are 0, I told you. So you have a bar, and a bar is again 0. So you have 0. So this way you can use the distribution theorem to simplify, right, things up. And you can use consensus theorem also. The consensus theorem, what it is, you have AB and its complement with other term, and then you have the product of these two terms. Then this term becomes redundant. So if you have one term, and with that term you have another term, and with that you have complement of that term, with that you have another term, and then the product of that two terms becomes the redundant. How is it done? So the theorem says it is nothing but AB plus A bar C. This becomes redundant. So how to prove it? So you can write it as AB plus A bar C plus BC right, and into A plus A bar. Now let us break it up. AB plus A bar C plus BC ABC plus BC into A bar BC. Now if you take maybe AB common, you have 1 plus C, and if you take A bar C common, you have 1 plus B. And I told you 1 plus B or 1 plus C is nothing but 1. So you have AB plus A bar C. Understood the proof? So this is how you get the BC as redundant, right? You have a reverse or dual of this consensus theorem. So this is proof of consensus theorem. And there is a reverse proof, which you call as the transposition theorem. What it says? Just the reverse of it. What it says is that if you have AB plus A bar C, then it is nothing but A plus B times A plus C. Now I told you, using distribution theorem, if you have common, you can take it out and multiply the other two terms. So it is nothing but A plus BC. And I told you A plus BC it can also be I think I wrote it correctly, right? Sorry. This is just a proof. But if you want to understand this, then just let me correct it. So what the transposition theorem says here is A bar plus B into A plus C. Yes. This is what your transposition theorem says. So if you break it down, this term, you get A bar A plus B A plus A bar C plus BC. And now I have to prove this. So what can I take common is so I think I wrote it correctly, right? So let us try to prove A bar plus B into A plus C, right? So what we are getting, A bar plus BA plus A bar C plus BC. So A bar is 0, right? We know already. So now B times A plus A bar C plus BC. Now we can use the consensus theorem here, that if you have a term with another term and the complement of that term with another term and the product of the two, then this term becomes redundant by using consensus theorem. Okay, then we have BA plus A bar C, which is nothing but the actual term. So this is nothing but the transposition theorem, which is just the converse of the actual consensus theorem. And consensus theorem, we have actually proved it, so we can use it. And the distribution theorem is also helpful, which says A plus B and then A plus C is nothing but take the A common plus BC. So this is the distribution theorem. And this is the consensus theorem, where you have a variable with another variable and the literal actually plus A bar, the complement of that variable with another variable, plus the product of the two different variables, then those two variables become redundant. That is the whole point of the consensus theorem, or its converse. And you have the very useful De Morgan's theorem. And I told you the rule of redundant literals, that if you have A plus A bar X, then you can treat it as redundant, which becomes A plus X. This is also a helpful tool. And you have Shannon's expansion theorem, which is useful for Carnot mappings for reducing higher order literals into simple small order literals. Now, why is it useful? If you want to find the Boolean expression for a large number of literals, right? More than 4. Then what you do using Shannon's theorem, that if it is a function of 4, you can write it as taking one variable out dot the function of 1, put 1 in place of A, and then write it as a sum of product forms, right? Or A bar dot function of 0, put 0 in place of A, and then BCD. Or it is SOP form, or it's POS form, which is nothing but A plus function of put 0 here, and then sum it with A, and then product it with the A bar plus function of 1 b c d. It is useful for reducing. You got the reduced order function but with higher number of terms, so you can reduce easily. Reducing a more number of terms directly is very tedious, so we broke it into two parts with smaller number of terms but higher smaller number of literals but more terms, so that we can see each term explicitly. Now we can combine and reduce individually. So this technique is helpful for both K-map and both algebraic reduction with reduced number of literals in each term, because one literal is taken out like this. And there is the De Morgan's theorem. So De Morgan's theorem I also need to write here. There is the De Morgan's theorem, which says that AB whole complement is nothing but A complement plus B complement, and A plus B whole complement is nothing but A complement dot B complement. So this is also helpful. If you break the inversion, then you have to replace the dot with the plus, or if there is plus in between, you have to replace by dot after breaking the inversions. Now using all of this, I need to actually make you prove some concepts that we have already derived earlier. We were telling just few times before the XOR and XNOR. The XOR was A B bar plus A bar B, and the XNOR was AB plus A bar B bar. Now I want to make you prove that if I take the complement of Y, you should be able to reduce it in this form. Try to find this should be same as this, because if this is Y2 and this is Y1, we know Y1, Y2 is nothing but reverse of complement of Y1, because this is XOR, this is XNOR. It is just the inversion, right? So if I complement Y1, I should get Y2. Now Y1 I complemented. Now try to use De Morgan's theorem and other laws that I already told you to simplify this expression to prove that it is nothing but this expression. Can you do? So first let us use De Morgan's theorem to break this and then into product form. I broke the inversion into two terms, among the two terms, so the plus got replaced by dot. Now if I again break it, the dot gets replaced by plus, and it is product with then it becomes A bar plus B, because double inversion of B is nothing but B, and A plus B bar, which is nothing but A bar A plus B A plus A bar B bar plus B B bar. B B bar and A bar are 0, so you get back B A plus A bar B bar. So it is proved, right, that the inverse of this function, which is inverse of the XOR, is nothing but the XNOR, which can be written as this. It is also written as A XOR B whole complement, and A XOR B is A B bar plus A bar B, whose complement is nothing but this, that we proved. Understood? So now you can prove like this. Similarly, we did another exercise which I told you I will prove later, that the NOT gate. I was using the NOT gate, right? In the NOT gate, I was doing what? 0 0 0 1 1 0 1 1. Sorry, in the OR gate, what I was doing, that Y is 1 1 1. Again, in the NOR gate, what I was doing, only when the terms are 0 and 0, that is both the terms are low, will I have high output. So can you prove? I know y2 is complement of y1, and let us write the terms in the mean term form, sum of product form. It is nothing but one how can I write m0, m1, m2 and m3, right? 1, 2 and 3. So how are they written in the mean term form? They are written as a bar b plus a b bar plus ab, which I told you to reduce. And what you will get, you take a bar or what you take a common out of these two terms, and you get b bar plus b, and you have a bar b, and b plus b bar is 1, so a plus a bar b, and by rule of redundant literal you can eliminate that. Please understand that the rule of redundant literal only eliminates one small literal from the term, not the whole term, like it is done by the consensus theorem. Consensus theorem removes the whole term, if you remember, but the redundant literal only removes a bar, so it becomes a plus b. Now try to prove that the NOR gate is also not of inverse of the same. So let us write in mean term form, which is a plus b. I hope I am doing. Yes, this is a plus b, right? But I need to take the lower terms, right, in the mean term form. So if I want to write in the mean term form, it should come as a plus b bar plus, sorry, so in the mean term form I should take the higher ones only, right? Sorry. So it is a bar b bar. This is sum of product forms, mean terms, right? So I take the one. So this is a bar b bar. So try to prove this is y2, right? Try to prove y2 is nothing but y1 complement. So y1 was a plus b. So a plus b whole complement. If you use De Morgan's theorem, you will get a bar dot b. So we are proving it correctly. But you see that while you try to prove these things, you need De Morgan's theorem, you need rule of redundant literal, you need the distribution theorem. So these 3-4 theorems are very useful. Hope you understand, you are with me up to this. So these 3-4 theorems you will need everywhere if you want to prove even simple things. So during the performing the Boolean reduction or Boolean simplification, logic simplification from a maybe a complete term to a reduced form, which you call as non-canonical form, you need to reduce it using these theorems only. Otherwise, you cannot reduce the Boolean expression. So first, I will take only 3 examples, and that will take 5 minutes, and then I will leave you. Okay, so example 1, maybe I can write y as a bar b c bar plus a b bar c bar plus a b bar c plus a b c bar plus a b c. Try to reduce this. So what you will do, you will group the common terms. So you have a b c bar. Since we are late, I am doing it fast. Okay, a b bar take common, c bar plus c, and then you take a b common, then again c bar plus c. I told you c bar plus c is nothing but 1. So what you get, a bar b c bar plus a b bar plus a b. Then you take a common, a bar b c bar plus a common, b bar plus b. What you get, 1. Then a bar plus b c bar plus a. Now you remember, sorry, a bar b c bar plus a. Now you remember the rule of redundant literal. A plus A complement of something, this A bar becomes redundant. Understood? So it becomes A plus BC. How? Again you can understand A bar B C bar plus A. Also if you want the proof, I can add with this reduced expression any of the original expression terms. Why? Because A plus A is nothing but A. So if I reduce this term to find that it is A bar B C bar plus A, I can add any of the terms with this original reduced term because OR will remain the same. Because if I find A plus B and then if I add with A, then it will still remain A plus B. Or even if I add A plus B, then it will again remain A plus B. So I can OR with any of the terms. So if you see, if I add, even without knowing the rule of redundant literal, if I added this term, A, B, C bar, then I would have got A, B, C bar is this term, right? I will highlight. This term. If I add A, B, C bar, then what I get? Try to leave A as it is and try to take B, C bar common. Then A plus A bar will give you 1, which is nothing but A plus B, C bar, which is same as this. So without even using the rule of redundant literal, you can just use the law that even with adding with similar terms from the reduced term, with the reduced term, if you add similar terms from the expression, then the term remains same as y. So using this also we can prove. So it is A plus B C bar. Use either the rule of redundant literal, it will save your time, or try to prove it by using these kind of concepts. Or if I want to give you another small maybe example, this you can directly use, take A common, and then so I told you anything with 1 gives 1. If you OR anything with 1, it gives us 1. So it gives us A. This is also one of the example. Then let us take another example. The distribution theorem you must recall. So I told you if anything is common, you can write it and add it with the product of the left out terms. So please recall distribution theorem. Okay, understood? Just the application of distribution theorem. And then if you remember, we have the multiplex. So multiplex is nothing but if you have it just is use of selected lines. Let's say n number of selected lines to marks the outputs, to marks the input to one output. So this is output, this is input, and how many number of inputs? 2 to the power n, right? Because each selector line can be 0 or 1, 0 or 1. So every selector line value will correspond to one of the output. So if I have n bits and 2 to the power n options, I have this 2 to the power n options of selecting the selector lines corresponding to one output. So the number of outputs, or sorry, number of inputs is 2 to the power n. Because such inputs can be selected based on the selected value of the selector lines. So maybe you call it input, and this is the number of selector lines. This is also a form of input that the user has to give so that this input function, input value is chosen. And the output keeps toggling between different inputs. selecting. So if you have maybe two number of selector lines and you have 4, so we call it 4:2 marks. Also, you may have one only selector line and two inputs, because if this is 1, this is 2 to the power 1 or 2 inputs, and this is single output. So let us draw, if this is A, this is B, and this is S, or if you write it as D0 or D1 as the selections, so S being 0, you get at output D0, and S being 1, you get D1. So what is Y? Y is S bar, writing in the sum of product forms, S bar times D0 plus S times D1. See, if S bar is 0, you have this term go off and your output is D0. For S is 0, and for S being 1, your output Y becomes S1. Sorry, D1. This is the function. You write in min term form that this is S bar D0 plus S D1. Min term representation, min term SOP representation of a 2:1 marks. Similarly, if you try to for 4:2, then what will happen? S0 and S1 are the, sorry, S1 and S0 are the two selector lines. For that you have 4 possibilities: 0 1 1 0 0 0 0 1 1 0 and 1 1 D0 D1 D2 D3. You have 4, right? And S1 and S0. So what you get? You have S1 bar S0 bar D0 plus S1 bar S0 D1 plus S1 S0 bar D2 plus S1 S0 D3. So this is the equivalent function Boolean expression for a 4:2 marks. So this is all. Similarly, we have 8:3, like 3 selector lines and 2 to the power 3 available inputs for selection. Accordingly, you can draw the truth table for maybe S2, S1, S0, and Y for these marks. Where D7, D6, D5, D4, D3, D2, D1, and D0 are the 8 output available inputs. So these are 8, which is 2 to the power 3, and this is 3. 3 selector lines, so 2 to the power 3 available inputs, and this is the marked output. So you have individual states for that. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 and 1 1 1. So 1 2 3 4 5 6, sorry, 1 1 0 7, and you have 1 1 1 8. So for that you have D0 D1 D2 D3 D4 D5 D6 D7, 8 possible outputs for based on the available selection inputs, and you can write it as in min term form, min term SOP form, as Y equal to D0 into S2 S1 S0 bar 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 plus D1 into S2 bar S1 bar S0 plus D2 into S2 S2 bar S1 S0 bar plus D3 into S2 bar S1 S0 plus D4 into S2 S1 bar S0 bar plus D5 into S1 S0 sorry S2 S1 bar and S0 plus D6 into S2 S1 S0 bar plus D7 into S2, S1, S0. So this is the equivalent Boolean expression for the 8:3 marks. I hope with this you understood the basic concepts of deriving or developing the logic expressions for the various logic circuits, and with this we conclude the session, live session on the digital circuits. And please recall all the discussed formulas or expressions that you will need for developing the simplified logic expressions. And the simplified logic expressions are very useful to simplify the hardware construction and reduce the complexity in developing such expressions in the real world implementation form. So that with this we conclude the session. Thank you.